Hi guys, welcome to Learning Electronics Repair and welcome to 2024. Yeah, so I think we should start the year with the answers to the quiz that I set, well, last year. Yeah, must have been ages ago. And of course, we all need answers. Yeah, we always need the answers. We need answers. Answers to everything. Yeah, life, the universe and everything. Well, I'm not sure I can quite solve that one, but I can explain the answers to these questions. So the first one, if you have long memories from last year, yeah, we made a circuit with two resistors in series. They were both 10 mega ohms. I put 30 volts across the resistors. Yeah, they were 30 of last year's volts. We'll have 30 of this year's volts now. There we are, 30 volts across the resistors. And the question was, what's the voltage here? Yeah. Well, Ohm's law tells us that the voltage here should be half the voltage here because the two resistors are the same value. This is a potential divider. So let's see what we've got. Okay. So from the negative to here, well, I have 10 volts. Okay. So I have 30 volts here and I have 10 volts here. So that's the answer to the question, is 10 volts. So if I've got 10 volts across this resistor and 30 across the total, I must have 20 across this one, yeah? No, I've got 10 volts. So I've got 10 volts across each resistor and 10 volts missing. So does that mean Ohm's law is actually not correct at all? Well, it doesn't actually. What is causing this to happen, and I will prove it, is that our multimeter is a resistor. So to measure voltage, some current has to pass into the multimeter, yeah? And it's a very high resistance. It's actually 10 mega ohms. So the resistance of my meter, when I connect it to the circuit, is 10 mega ohms. So what that means is, if we look at our circuit again, if I connect my multimeter here, okay, to here, I've actually got the equivalent of 10 meg, okay, another 10 mega ohms, and then across this one another 10 mega ohms. That's the multimeter in parallel with the resistor. So what I actually have now is 10 meg and 5. Two 10s in parallel equals 5 meg. So the circuit equivalent becomes this: 10 meg, 5 mega ohms, plus 30 volts, 0 volts. So this resistor now is magically twice the size of this one. So it gets twice the voltage across it. So we get 10 volts across here and we get 20 volts across here. But when we come to measure this one, well, we've now actually connected our multimeter in parallel with this resistor. So this is now 5 meg and this is now 10 meg. Yeah, so it's the other way around. So now the 10 volts is here and the 20 volts is there. And the best way to prove this is if I measure the voltage across both resistors at the same time. Let's see if I can do this without some crocodile clips. You know, I always need crocodile clips. Crocodile clips are not overrated, okay? We need crocodile clips. So I'll attach this meter to the green wire and we'll attach it to here. Okay? And we have 10 volts. We know that. Now if I get another multimeter, okay, put it onto volts, and assuming the input resistance of this one is the same as that one, so they're both 10 meg, what do you think will happen? Well, it's easy to find out. So we go from here to here. And look, this one is now reading 15 and the other one magically changes from 10 to 15. Okay, And that's because we've balanced the circuit, the potential divider. So now we have our original circuit, 10 megaohms, 10 megaohms, and connected across this one as one of our multimeters. Yeah, one of our multimeters. That's 10 meg. And we have our other multimeter connecting from here to here, which is also better draw the resistor, 10 meg. So we've actually got 5 with these two in parallel and 5 with these two in parallel. So what have we learned? Well, we've learned this can be a little bit devious with questions sometimes. We've learned that Ohm's law really does always apply, even when it looks like it doesn't. And we've learned that our multimeter, in some instances, can actually affect the voltage you're reading just by reading the voltage. And this occurs when there's a very high resistance in the circuit. So I hope you got that one right. If you didn't, or even if you did, I hope you enjoyed the explanation of it. Now let's have a look at question number 2. Okay, so here's question 2. We have an op-amp circuit here. This is wired as an inverting amplifier. So we have 2 resistors forming the feedback. Basically, this is the feedback resistor. This is the input resistor. This is 1K and this is 3K. So because the feedback resistor is 3 times the value of the input resistor, we get a gain of 3. And we can see that. So we have an input at the moment like about 1.2 and the output is about 3.6. So it's giving us what we expect, a gain of about 3 times. And we can clearly see that the output is inverted compared to the input. It's an inverting amplifier. And the question was, what will we see on the output of the op-amp if I turn the power off? So first of all, let's try it. Well, you can see there, what do we get? The input and the output are now both the same. So it's no longer inverting signal, and the amplitude of the two now is the same. Okay? So that's the answer. But why does this happen? Well, the output that we see from the op-amp is not coming through the op-amp because the op-amp has no power. And I can prove this quite readily by just removing the op-amp chip. Okay, so we get the op-amp chip. And we'll take it out of the board. Okay, it's gone. And we still have the same output. Okay, so the output is the same now whether the op-amp is there or not. Let's draw this and that'll become quite obvious if it wasn't already. So here is our circuit. Our op-amp, out, inverting input, non-inverting input. This is connecting to ground. We have our power rails, plus and minus, it was 15. And then we have our feedback. So we have an input resistor here, which is 1K, and we have the feedback resistor here, which is 3K. And this sets the gain. Okay, this is in, this is out. But if we turn the power off, the op-amp's no longer doing anything. And as you can see, I can even remove the op-amp and the output is still the same as the input. Well, let's remove the op-amp from our circuit. So we have in, we have a 1K resistor, then we have a 3K resistor, and then we have out. So if we remove the op-amp from that circuit, that's exactly what we've got. So obviously the signal just goes through the 2 resistors, and because the input impedance of our oscilloscope is so high, what we see on the output is the same as the input. We don't see any drop in voltage due to the resistors. So that's the answer to number 2. Switch the power off and the output is the same as the input. How about question number 3? So in this question, I took a 50K slider potentiometer. The fact it's a slider is not relevant. The same thing will happen with a rotary potentiometer. The reason I use the slider is because it's easier to see when it's in the middle, basically. Okay, it's easy to say, yes, that's in the middle. In fact, it's a little line down there, it's in the middle. So the question was with this one, we applied 10 volts across the potentiometer. What voltage do we see on the slider? So let's have a look to see what the answer is by trying it. So we have 10 volts across our potentiometer. What's the voltage on the slider? Well, it's 1.6. Okay, so it's about 16% of the voltage. It's not half, which a lot of you expected it to be. It's much lower, yeah. But this is a bit of a trick question in the way, because if I reverse the polarity here, okay, again we have 10 volts, and on the slider we now have 8.3. okay, so the answer is it's about 16% or 84%, depending on which end you put the ground. Why? Well, the potentiometer is effectively a potential divider. The slider forms the junction effectively between two resistors. Here, this is your slider, but because it's a slider, you can move it up or down. So what you actually have is a resistor with a slider that you can adjust. Okay, now if we put 10 volts here and we put 0 volts here, and we move the slider to the center, you would assume that what we'll get is 5 volts, because the resistance from here to here equals resistance from here to here. And that is correct if you have a linear potentiometer. But this one isn't. I showed you all clearly the markings on this one. V50K, that's 50K, AX2. The X2 tells me it's a double gang, but we're only using one, that's not relevant. But the A tells me that this is a logarithmic potentiometer. Okay. So with a logarithmic potentiometer, it doesn't vary the resistance evenly. It does it on a logarithmic scale. So what that means is we can get some crocodile clip leads again, because we'll need them. So we'll connect to the wiper. Okay, we're on the wiper there. I'll connect my multimeter now to the end of the track, one end of the track. We'll go to resistance range. And you can see that the value in the middle is about 7K. If I go all the way across the track, it's 46, 47. It's close to what we'd expect for 50, okay? But look, if I come to this end, if I move this a little bit, the resistance changes. If I move it the same amount again, it changes by quite a bit more. So if I go to here, it's now 2K. In the center, it's now 6K. So as I get towards this end of the track, a small adjustment, look, it's gone from 46K to 43K. Now it's gone to 33K. So you can see that the effect is not linear. You get much more change of resistance at this end, okay, than you do at the other end. Now it's only changing by small amounts, hundreds of ohms. Okay? The reason we have these, by the way, these are normally for audio circuits. It's one of those strange things with audio and power that to get twice the volume, you need 10 times the actual power or voltage or current. It's probably more correct. Yeah, wattage is probably even more correct. So that's why we have these types of potentiometers. So those of you with sharp eyes recognized from the code on there that this is a logarithmic potentiometer. Okay, and those of you who didn't get it right, well, now you know what to look for. So if you want a linear potentiometer, and I'll show you one. This is a linear one. You see this says B50K. So we get A and B. The way I remember it, I always think A for audio, and audio uses logarithmic scales. That's the way I remember it. There's probably some better way, some better mnemonic. Guys, comments below. Anyway, that's the answer to that one. And if you got it wrong, well, I'm sure you've actually learned something now. So it was still good. And the last question, the mystery component. So when we add the mystery component to our circuit, which is this circuit, 1K, 10 microfarad, mystery component, little speaker. Okay, when we add that, in one direction it bleeps, in the other direction it doesn't bleep. And the question is, what's the mystery component? Well, let me show you something else that's happening with this as well, and then I will explain it. And a few of you got this right, pretty much, so well done, guys. The ones of you who didn't, well, you're going to learn something interesting now. So you can see my power supply there set to 12 volts. But if I turn the voltage down, see, it stopped. Yeah? So it needs more than 10.8 there it just starts, yeah? And the frequency changes with the voltage, okay? So what's happening here, and that should give you a hint. For this circuit to behave in this way, we need a component here that will break down at a certain voltage. So the capacitor charges up via this 1K resistor, which takes a finite amount of time. So the voltage here increases. Not linear, but sort of like that. And when it reaches enough voltage for this device to break down, this suddenly conducts and it discharges the capacitor through the speaker. And that makes a click. Okay. When the voltage across here drops to a certain amount, then this will stop conducting and the capacitor can charge up again. Okay. And you just saw in my circuit that 0 volts, 12 volts, and about 10.8, I think it was. So on my circuit, the device doesn't start making a noise until the voltage gets above 10.8. Okay, and then it starts doing this, so it's discharging the capacitor. But once the capacitor discharges below 10.8, as we've seen by turning the power supply down, the device stops conducting. So the capacitor charges up again and it starts to make a noise and off again. And each one of these is a click, 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 click. And if you do it rapidly enough, then you get a tone, which I was getting. So what device will do this? Well, there's a few that will do it, but we need to consider this, the voltage. So a diac will do this. So a diac is like a thyristor without a gate that switches on at a certain voltage. In fact, it's more like a triac, it's both directions, yeah. So a diac will do it. There's a device called a tunnel diode, a rather strange device, but a tunnel diode will also do this. And there's another device that will actually do this, which you may not consider, but it is. It's not even a semiconductor device. This is a neon bulb. So the neon will not strike until it reaches sufficient voltage, but once it strikes, electrons are flowing through the gas, it's glowing, and it will keep on glowing to a lower voltage. And this property is very important in electronics. And it's called hysteresis. Or hysteresis. I say hysteresis. Comments. So we need a device here that will break down at a certain voltage. But a neon won't break down till about 90 volts. Yeah, a diac is usually something like 36 volts, depends on the diac, but something like that. We need to do it at a lower voltage. So what did I use? Let's have a look. That's the speaker. That could have been an outtake, but hey, it's New Year's Day. I'm working New Year's Day for you guys, by the way. I didn't have time to do this on New Year's Eve. I'm not working for too long, okay. So, let's see what's inside here. Okay. Here we go. Well, actually, it's a transistor. This is a 2N5551. Okay, transistor. And if you notice, the middle pin, which is the base, is not connected. I'm only using the emitter collector. So with a transistor, NPN, you can only do this with NPN transistors, by the way. If we connect our transistor here, and we connect it in the normal direction like an NPN transistor to our speaker, to ground, because the base isn't connected to anything, the transistor is switched off. So in this instance, nothing happens. But what happens if we put the transistor in the wrong way round, back to front? Yeah. Well, I think you already know what happens. 0 volts. We'll connect our transistor backwards. Okay. Let's make them look more like transistors. There you go. Now you might think that the transistor won't conduct because the emitter is the higher voltage than the collector, and you'll be correct. But it can only withstand the voltage to a certain point. When you reach enough voltage here, then current will flow through the transistor. And that happens when this capacitor charges up via the 1K to a sufficient voltage. Yeah, the curve I just showed you. Now the transistor breaks down. But once it breaks down, it starts to discharge this capacitor. The voltage suddenly drops. And when it reaches a voltage below, you've seen about 10.8, the transistor stops conducting. And so the capacitor charges up again. And that's why it makes a noise on the speaker in one direction. This is an NPN transistor, and I'm using the reverse tour. Told you it was New Year's Day. I'm still half asleep. Yeah. So we're using the property of the fact that the transistor will break down in the reverse direction at a certain voltage. You can't do this with all transistors. Some work better than others. I use this one. Apparently you can use a 2N2222. But I tried this with 2 or 3 of them and it wouldn't work. So experiment if you want to build this with different transistors, but you can see this one worked really, really well to demonstrate the property. This breakdown property, by the way, is what a tunnel diode does. Okay, I think a tunnel diode is a symbol without looking it up, so I'll make a fool of myself. I think that's the symbol, which is a rather strange device. This property is used in things like sawtooth oscillators. This is not just a trick for the sake of a question. This is actually used in some instances. Also, if you make the capacitor here much larger, say 330 microfarads, and you change the speaker with a LED and possibly a resistor in series with it, the LED will flash. Okay. There's a name for this type of circuit. It's called a relaxation oscillator. Okay, so I hope you enjoyed that, guys. I hope you got some of the questions right, and if you didn't get them right, well, it doesn't matter because you've all learnt something today. Okay, so until next time, Happy New Year. See you all soon on Willy Electronics Repair. Ciao for now, guys.